If everyone take their seat, please. Welcome here on this very nice day at the Metalot facilities again, amidst of where we always have these or tend to have these sessions, amidst the metals that we're working with and on. So today we have actually a special program because we're going to extend our view a little bit. But before that, just a couple of, how do we say that, household remarks, I would say. Should there be a fire other than planned today, then there's a big exit door over there. There is one exit door in that corner and one in the middle there. Don't run upstairs, because there's only one way back then. The place where we collect in case of an emergency is outside near the entry of the parking lot where you come in. So, that is the must-do points already. Today we also have, again, like we had before, 2 online presentations as well. That means we will have international visitors, and it also means that our international community is growing and growing very fast. Today we have more than 25 people also online participating in these Metalot at Work sessions, which is a good sign. To play nicely by the rules, if we have had presenters here, be it on stage or online, I'll ask first maybe the online people if they want to ask a question, because we need to arrange then that we can hear their question and they can hear our answer. Michael is going to make sure that everyone understands each other. And then we'll have also live the potential to ask questions as well. Before you ask a question here, make sure that you always have the mic, otherwise the online people can't hear you. So, coming back, I said we try to go a little broader today. In the past 1.5 years, we have gone the iron cycle, so we have combustion there, we have reduction facilities here, we have the wet cycle here. We even try, and we discussed last time also, doing electricity in our mix as well as an end product. That's all nice and good. And that's actually big support to energy transitions, because the discussions now move from speaking about individual equipments to total solutions you can provide to society, which is a totally different discussion. It feels like moving from the technology push side towards the market pull. You have to tell now and be able to explain to the market why this was good or is good, and the response is very positive. People start pulling you, which means you get very busy, which we all are, but it's also a big fun element of the job we're doing. It also makes us realize that, well, probably some of us, and I was one of them, a couple of years ago, thought, oh, this is fantastic. We are the solution for energy transition. No one has a better recipe than we have. Really not. Until you reach this point where you start thinking in market traction, it's probably smarter to make the others understand that and say, you can think of us what we want, but we're part of a very good solution, which is a little bit more modest, but creates the effect on the other side that they really want to hear what you have to tell, other than that they think you're arrogant. Okay, enough of my talk now, because Jeff is already looking at me. I'm stealing his time, and it's only the first presentation, so we'll, now. Jeff, I already am announcing you. You're one of the leaders, I think, together with Philippe, who started this early on, kept going, and you took an interesting sidetrack. Today we're going to look at other metals. Not to say iron is finished, no, but it would not be smart to think that we're there. Yeah, so we should keep exploring. And one of the avenues is that you have gone, and pretty far already, because you're, well, probably even in some phases ahead of iron. Jeff, tell us more about beyond iron. And you said, I'm going to talk about aluminum.
I'll talk about more than metals than just aluminum.
Yeah.
But Thank you so much, Rahul. Really thank Rahul and Michael for the hospitality and hosting, and for Philip for really creating this community that we have now around metal fuels. It's really exciting to be part of this. So I was asked to talk about metals as recyclable energy carriers, looking beyond iron. And really from the start, our group really looked at this problem holistically, I think, really looking at the whole periodic table and trying to think of where the different solutions can lie. So it's very nice to come to Metalot, and I don't have to start with what is metal fuels and what is this idea of a circular economy. The main messages that I want to talk about today is really that beyond iron, we have the wet cycle, and specifically we'll talk about the technology that we've developed at McGill that is one way that we can use a bunch of other different possible metals that maybe are more mature in terms of the green recycling, or maybe can provide better performance for specific applications. If we have time, I'll talk a little bit about the techno economics and life cycle compared to the other major options that we're talking about. So looking at the periodic table, we can see that there's a lot of options for metal fuels beyond just looking at just iron. And something like silicon or aluminum, they provide very high energy densities and also getting to the sort of energy storage per unit mass that's on par with fossil fuels. So they can really address some of the energy density issues associated with iron. And we can, of course, burn those in flames. And we studied, in fact, my first metal flame at McGill was not iron. It was the first study we did was burning aluminum powder in hydrocarbon combustion products. And that really was the start of my journey into metal fuels. We've also studied iron, of course, and most recently, we've stabilized the flame of silicon powder. So we can show that all of these different metals could be used as possible energy carriers in the dry cycle. But we were actually inspired, and the first work that I did on metal fuels really came from this idea of propulsion, where metal-water reactions were used to make what's called the ALICE rocket, the aluminum ice rocket. And in that system, they basically take nanoparticles of aluminum mixed with water. I don't know why the GIF stopped playing, but we'll see if we can get it to go. Maybe it's hung up. There we go. Well. And so in this, basically a test tube, a strand of this aluminum powder filled with water, they light it at the top, and a flame propagates down through that mixture at centimeters per second scale, generating hot hydrogen. And so the exhaust of this rocket is hot hydrogen gas that's being exhausted. And we said, well, that's very interesting. We could use that reaction instead of to power a rocket. Why don't we use that to power and make an energy storage device? And so that's what we'll talk about today, is look a little bit more at this wet cycle. And so when we look at the energy densities of these different alternative metals, the three that I'm going to show today react very well with water. I mean, of course, sodium and lithium can react well with water, but in an extremely dangerous way, as we all learned in high school chemistry class. We're not going to look at sodium as an energy carrier. But these other metals, aluminum, magnesium, and zinc, work very well in our system, and they provide very interesting energy densities. And so to put that into real numbers, if you transport a liter of each of these metals, they produce heat at different levels, but for aluminum and magnesium, basically almost the same amount of heat as you get out of reacting, burning diesel fuel. Plus, you get the equivalent of 2 to 4 liters of cryogenic hydrogen. That's hydrogen stored as liquid hydrogen. So the energy density of transporting energy in terms of aluminum is much more effective than either hydrocarbon fuels or hydrogen as an energy carrier. And that's really the advantage of thinking about these things as the energy carriers. And so what we did is we developed a technology that uses supercritical water to react those metals, and that reactor can basically take these metals in bulk form. We're not talking about powders. These are millimeter-sized slugs, so 3 millimeters, give or take, in size. Think about the little pegs you put in your IKEA bookshelf to hold up the shelves. Basically, that's our fuel. And those pellets of fuel are completely inert and safe under room temperature conditions, normal atmospheric conditions. You can get them wet. You don't have to worry about any hydrogen explosion, which you would if you had nanometric powders. And then when we put them into our reactor, they all get digested under supercritical water conditions into the metal oxide, producing a stoichiometric amount of hydrogen and heat. So all of those metals can react and give you full reaction yield under our reaction conditions. So this was shown by my PhD student, Keena Trowell, some years ago. And here we're looking at aluminum, a couple of different alloys, magnesium, silicon, titanium, zinc, and zirconium. Those were the metals that we looked at, primarily from their energy density points of view, as well as thinking about what should be thermodynamically favored to produce hydrogen from those. And the dashed bars here show what is the maximum amount of hydrogen that you can produce per liter of the metal. If you produce that maximum amount of hydrogen, you also produce the corresponding amount of heat. So you can see that aluminum produces more energy per gram than zinc, for instance. On a volume basis, they're much closer because of the differences in density. And so then when we look at that, we can look at the reaction as a function of temperature. Unfortunately, the temperature scale didn't come up here. I think it's 200, 250, and then we're at 350 and 400 as these last two bars. So once we get above the critical point of water. And so for this reaction, basically aluminum and its alloys, we can basically get 100% conversion under those conditions. Magnesium a little bit below, maybe by 200 degrees Celsius, and zinc can also produce a stoichiometric yield under those supercritical conditions. So under those conditions, we can completely react those metals. Interestingly, titanium almost completely inert, and zirconium, a very low reactivity. Silicon metal also didn't show very much promise. So that means we can strike those from really looking at them further in the wet cycle. And so from this work, we said, okay, let's go and scale up and develop a project on this. And so working with a few different industrial partners, Siemens Energy, Hydro-Quebec, Rio Tinto, Teck Resources, and Agnico Eagle, which is a gold mine, we developed a project to build up a scale prototype of this. So we've now developed in the lab a continuous flow reactor. This is a picture from a few weeks ago, but basically here's the flow reactor. We have a water pump, a feed water heater to get us to temperature and pressure, and then a reaction cell, separation system, hydrogen separation system, and then an after treatment for the hydrogen. And we're now developing and demonstrating that we can get this reaction to work in a semi-continuous mode. In other words, continuous feeding of the water, separation of the products, generation of the hydrogen, and dealing with the hydrogen. But on the same side, we'll eventually bring in the injection, co-injection of the metal as well as the water and be able to demonstrate that this thing can work. So we're now looking to scale this up. This will be sort of on the order of a kilowatt once it's fully operational, and we want to go up obviously to industrial scales following that. So just to talk a little bit about the techno-economics and the life cycle of this process, we looked at this energy cycle as we know, and we're really going to look at the recharging part of this to really look at what are the most cost-effective metal fuels. So initially, we did a comparison of this aluminum cycle specifically for a remote mining application, although transportation costs are pretty much negligible, so you can almost apply this case study to any case. It's specifically interesting compared to liquid hydrogen when you have to do the transport and storage, however. And so you have production of the metal, which is your power storage step, shipping, moving the metal, towards where your application is, and then bringing back the oxides, reacting it in the reactor, producing hydrogen and heat, and then providing that to a different power generation system. And we did that comparison for aluminum. We compared that to liquid hydrogen as a possible energy carrier, and to liquid ammonia as a carrier where you can do it in two ways. You can either directly combust it, high NOx emissions is a problem, or you do a cracking step that has some energy efficiency losses. Won't go into all the details of that, but the basic story says that if you want to look at the fuel price that you're going to produce, it depends primarily on the capital cost. So at zero input electricity price, that sort of tells you the range of your capital costs, and we did this for a band of estimates. And then as you go to higher input electricity costs, obviously your fuel cost is higher. The steeper the slope, the lower the efficiency of that process. And so we can see that aluminum, this is estimated to be what it would be if we used inert anodes, so a green aluminum recycling process. We can see that it's a little bit still more expensive than diesel fuel when we look at it with the type of costs of renewable electricity that we have available in Canada. Obviously, if you can put in free electricity or negative price electricity, then we already can be cost competitive. And so that makes it seem interesting. And the more interesting case is that if we compare that to either liquid hydrogen or ammonia as an energy carrier, then basically we see they're all in striking distance of each other. And so that means that while those are the two options that are really looked at internationally for this problem of how do you store and commodify renewable energy, these metal fuels can be definitely competitive on a cost basis when we look at that life cycle. And so that, I think, is very interesting. And we then have adapted that and looked at what does that look like for these other possible metals. We looked at zinc, magnesium, and aluminum because they were the ones that reacted well in our system. And we find the same basic structure, right? There's a capital part at zero cost, and then there's an input electricity cost. That's the most important of the variable costs. And so we can see that there we see that the zinc metal is the cheapest of the three, aluminum in the middle, magnesium a little bit higher from the higher capital cost. But that's on a dollars per ton of metal. When we look at it in terms of dollars per megawatt hour of energy stored, then things shift around because of the higher energy density of aluminum. It looks like the lowest cost, and zinc metal comes up a little bit in cost. Very difficult to estimate the capex of a zinc smelter because zinc is produced in a co-production of a bunch of different elements from the concentrate today. It's not taking direct zinc oxide and doing that recycling process. So one high uncertainty is, what is this intercept? What is the cost of that reduction process, and can we do that cheaper? And that's, I think, an open question that we want to address. Also, just compare global warming potential here for aluminum. We've got diesel marked on there in terms of kilograms of CO2 per kilowatt hour of energy. For conventional aluminum production using Hall-Heroult process with carbon anodes, we can see right away it doesn't make sense from a climate change perspective. So the primary aluminum production in the current way is too dirty, too much CO2 intensity to be a good metal fuel. But when we look at it with inert anodes, basically eliminating those direct process emissions, we can get, again, into very low values that are, again, very similar on a global warming potential basis to liquid hydrogen or to ammonia. And again, the primary input is really the global warming potential of that source of electricity. So this looks very similar to that cost analysis because basically, again, if you've eliminated the direct process emissions, it's your indirect emissions from your energy that you put in. That's the primary driver. So with that, we can also say that on a life cycle emissions, these alternative fuels are also competitive to those options that are out there. So I think that's very important, and that gives us the opportunity to then say, hey, what about the other advantages? Safety, we don't have any toxicity like ammonia, and we don't have the same explosive concerns associated with hydrogen transportation and storage. I won't talk about that. So to give time, if there's questions and discussion, I can end here. Basically, the message that I want to give out is that beyond just burning these metals for heat, we can do this reaction in water to produce heat and hydrogen. If you do that with supercritical water, you don't need to use metal powders. You can really move beyond into scrap. We've done this with aluminum cans cut up, and basically any type of scrap. You can use this reaction to digest that metal and produce hydrogen and heat. And that opens up some very interesting opportunities for using waste resources today and maybe bringing them back into the value chain. And so we can see opportunities both for a tight circle using fresh, neat metal fuels that are in a closed loop, but we can also see it as part of the bigger circular value chain of the economy as we transition. And I think that's a really interesting opportunity that this whole metal fuel concept can build. So with that, I'd like to thank you for your attention and just thank our sponsors who supported all of this work. And then just put up a picture of my great team, who's the ones, of course, who do all of the work, and I just get to talk about it. Thank you.
Thanks a lot, Jeff, for this fast-track overview. Really impressive. I was actually preparing a question to ask you, if you've done all that, how big is your team? But you already showed us.
Yeah.
Thank you very much for that. Any questions for Jeff online? Do we have any hands from people? No? Any questions over here? On magnesium? On zinc? Who offers more? Oh! No. Wait until you have the microphone.
Hello, Jeff. This is Laura from University of Liège. So I think you mentioned a very key point there, circularity. And my question is, if you ever integrated in your cycle analysis waste metals?
So we haven't done a waste metal stream specific techno-economic analysis or life cycle analysis. I think it'd be useful to do. Almost always when you do like a waste to energy, I mean, if you don't include the life cycle emissions of producing that metal, because presumably those are allocated to the primary usage of them, then for our process, there's basically no direct process emissions. I mean, a small amount for the infrastructure associated with building the facility. I think actually we have the stack here. So if you look at doing this, if we eliminate the need to generate the aluminum, that's the energy, that's the electricity part. The shipping part might be there, might not, if we're using it as a fuel. And then the conversion and the conversion efficiency, you can see it's a very small amount of global warming potential from the capital cost of the equipment. That's the power generation equipment itself. So basically, because there's no direct process emissions, you can have very, very low effective impact from using scrap or waste, 100%. And also presumably low cost.
Any other questions? Otherwise, we'll move on with the program. Jeff, thanks a lot.
Thank you.
Again, an applause for you.
Thank you very much.
Then I would want to ask Thijs Hazenberg on the stage here. Thijs, you have heard aluminum was mentioned by Jeff. You're going to tell us more about combustion of aluminum.
Yes, I'm going to tell something about aluminum combustion.
Before you start, I want to finish one thing maybe.
Oh.
TU Darmstadt recently also joined as a member of the community, which is fantastic. Also a reason, of course, why they also want to present what they do. This is an excellent opportunity, of course, on this. So, yes. Thanks a lot, Thijs.
Yes, so I'm going to talk about aluminum and then more specifically about aluminum steam combustion. Quite a bit of it is also applicable to the aluminum combustion in air, but the focus here will be mostly on steam. First of all, I would have to thank Jeff for giving exactly the presentation that I was anticipating, because I skipped some of the economical analysis and it was there exactly in the manner that I was anticipating. So this I can almost skip. In Eindhoven, I have done a lot of research for iron, and now I'm in the aluminum stack research. Why? Well, one thing is that the energy density of aluminum is much higher than that of iron, which could make it more interesting because that means less space needed and less weight needed to transport the fuel around, possibly leading to lower transport cost. So this is some of the earlier work that we done in Darmstadt, where we have a methane flame, and then in the exhaust gases we are trying to burn individual aluminium particles and trying to analyze this. Or, as Jeff also already showed, was the aluminum ice product work, which is done in Canada. Okay, then a little bit more specific to what we are interested in. So our idea is we want to combust aluminum in steam. This means we combine steam with dispersed aluminum. There we let it react, and the output will be heat and hydrogen. The heat can be used to generate power, and the hydrogen could be a very valuable item for the chemical industry, because a lot of the hydrogen currently produced in the chemical industry is from, for example, methane cracking, which still releases a lot of CO. Well, how does then a typical combustion of a single aluminum particle look like? We ignite the particle, we then get these bright spots. If we look very carefully on it, they dance around, and you see a little bit of this globe around it. And as we are mostly focusing on fundamental research, we are going to investigate a little bit on what's going on over here. And okay, this is examples, of course, with water vapor there, but we could also do the same thing with oxygen. So you would just replace the water vapor by oxygen. You will not get the hydrogen anymore, you will only get heat, but you will get more heat. Why we specifically choose for combusting in water vapor comes a little bit later. So if we look at it from a more of a viewpoint, zooming out a little bit, then on the left-hand side, what you can see is we have an aluminum particle, and you get these bright spots dancing around. And what tends to happen is that these spots move around. And if we do a little bit of a more fundamental study into it, this is the aluminum oxide that's on the particle, and viscous forces attract the aluminum oxide together and the aluminum main particle together. So we have a little bit of a surface reaction generating the aluminum oxide on the particle. Then on the right-hand side, we also see that we get a far more complicated physical phenomena that I will discuss a little bit more in detail, and that's we get like a sphere around it, and in this sphere, reactions happen. And how does this occur? We have the oxygen coming in from the environment, or the water vapor coming in from the environment, and the aluminum that's being evaporated from the particle, because the particle is reaching temperatures of over 3000 Kelvin, or well, a little bit lower, 2700 roughly, where the aluminum starts evaporating. So you get an evaporation process away from the particle, and you get the oxygen coming in from the environment. Then, at this red dashed line, the oxygen, or the water vapor from the environment, reacts with the aluminum being evaporated, and a flame front forms because there the aluminum oxide resides. Then you get heat transport from this flame around the single particle towards the particle surface, heating it up, driving this evaporation, and at the same time you get some of the heat convecting or conducting away from the particle. And in our specific case, where we do the combustion in water vapor, we get hydrogen as a product, so the hydrogen would also be leaving this flame front. Finally, you have the aluminum oxide being formed inside the shell around the particle, and this aluminum oxide can do two things. One, it can move towards the particle by thermophatic forces, or it moves away. When it moves away, what happens is that you get nanoparticles, and then you have nanoparticles in the exhaust. And this is one of the challenging things about aluminum combustion, because if you have nanoparticles, these are difficult to capture, which really hampers their recyclability. Which is actually one of the main challenges within the project, because what we want to do is we want to maximize the deposition of the aluminum oxide that's formed inside of this flame front around the particle, on the particle, because if we can do that, then we can recapture the entire particle, which is micrometers in size, and have a 100% recyclability. And then this is specifically for our case. Our idea is, okay, so if we use steam, what we will do, steam has a higher heat capacity than air, so we will reduce the flame temperature a little bit, bringing it lower, closer towards the boiling point of aluminum, and at the same time, if we would increase the pressure towards 6 or 7 bars, then the aluminum vapor pressure becomes roughly equal to the flame temperature, so the flames should move towards the particle surface, and then most of the aluminum oxide, is our idea, should arrive at the particle. And then what has been done before, so one of the leading people for single particle combustion of aluminum is Fabien Halter's group in France, who has made this levitator, and he has mostly done a series of laser ignited experiments with single particles of aluminum in either air or carbon dioxide, which is also where the video came from. But then the challenge arises for us, because we are interested in steam, and the problem is, okay, if you want to have 100% saturated steam, you need elevated temperatures of over 100 degrees C to do this. So our idea is to develop a new burner where we do non-premixed hydrogen combustion, and then in the exhaust gases of the hydrogen combustion, so water vapor, we would have this experiment. So we would shoot particles here from the center up to this flame, and then we ignite it. By varying the dilution ratio between, or the flow rate of the hydrogen and the oxygen a little bit, we can control the temperature a little bit, and we can possibly also insert something like argon or nitrogen, which is mostly inert, to control the dilution of the exhaust stream. And then when we have done that, we want to focus towards aluminum frames. So if we start understanding a single particle, we want to go towards flames. And again, this is work that's been done by Fabien Halter's group, and they studied flames in air. But what we want to do in the future is we want to progress towards doing this with steam. On the modeling side of things, we have already started to develop a model to describe this. So we have a single particle which has this aluminum lobe next to it. We can describe the diffusion processes inside of this particle layer. And then what we have now done is we have validated this model against results from either Fabian's Halter's group in France or other research by Beckstedt's group. And what we get is a reasonable agreement. So we were happy with that. And then what we want to do is a similar thing as Eindhoven has done back in 2019 and 20, is develop a single particle or a flame model, which is now kind of ready, but it is not yet published. So please don't take pictures and redistribute it. And what we get is something very interesting. So if we have a lean aluminium steam flame, we get that this particle starts igniting, which is the solid black line. Then it melts, where the temperature remains constant for a bit. Then the melted aluminum starts increasing in temperature, and then you get a separation because the aluminium starts to evaporate. So you get a flame developing around it, giving the very high temperatures of approaching 5,000 kelvins. We have some asterisks over there. Too much detail for this presentation. And then the particle remains at the boiling point and remains constant until it is fully evaporated away, or the aluminium is fully evaporated away, which gives this rather different flame compared to normally. And then if we go to rich flames, what actually happens is that at some point the oxygen in the environment is gone, and then what will happen is that the aluminium will only evaporate into towards the environment, and then you get a lot of nanoparticles. So this is generally something that you would like to avoid when you do aluminium combustion. Of course, a lot of this work is not done by myself. It's actually done by a rather big group for the ACE-Team project, or the A-Team project team. So we have Johannes, Stefan from RSM, or I'm bad in names, Didi, me, Andreas, and Christian, but now I forget the people from the other group because we are doing it together with RSM. Come to me after the presentation if you want to know the names. Yeah, thank you for listening.
Okay, Thijs, thank you very much. Can I ask if we have any online questions for Thijs? Not yet? Ooh.
Do you experimentally validate your hypothesis that product surface deposition on the aluminum droplet yields a micron-sized product?
Currently not yet, because we don't have high pressure experiments with steam running yet. So we are now developing the setup. Initially we want to perform the experiments at atmospheric pressure. When that's behaving, we want to see if we can increase the pressure towards 5, and hopefully in the end, I believe 10 bars is the goal, but we are a little bit skeptical about safety, 10 bars steam and hydrogen. So hopefully yes in the near future. That's all I can say. Hopefully yes.
Any questions from the audience here? Yes? We can probably this one.
Hi, Bram Hakstegen. I was wondering, you mentioned the nanoparticle formation must be controlled. Can you compare that with a combustion engine, the amount of particles, or what is the order of magnitude?
So it can be quite significant if you do not control it at all. You would do combustion, for example, in steam, then most of the particle will actually evaporate away. And then you will have basically, well, not the entire particle mass, because we still have, like here you will get these alumina oxide lobes. The evaporation temperature for those is much higher, so they won't evaporate. But anything that isn't already on the particle during the initial stage of combustion will effectively evaporate away, and then nanoparticles will form in the shell and they then diffuse away. So you really would have to control it by going up in pressure, otherwise you will lose, I think, probably in the order of 90% of the mass if you're not careful.
Philip.
Thank you, Thijs. So you did these simulations. Can you give an estimate of how much, let's say, how much can you go in the sense of the minimum amount of particles, of nanoparticles you lose if you're using the water high pressure situation?
Numerically, you can go to 0 effectively.
Really?
But that's numerically. What we do in the model is that we assume we always will have this flame sheet around the particle. And you will always have some kind of evaporation from the particle surface. And if you would start increasing the pressure, the flame surface will just move towards the particle. Because of the increased pressure, you will have more mass being diffusing towards the particle surface, but at the same time, the distance between the flame sheet and the particle will tend towards 0, driving the evaporation, the evaporation rate up, because of the gradient effectively going towards infinity, sorry. So numerically, it will behave and just go towards 0 nanoparticles. In practice, at some point, you will not be able to sustain a flame which is like a couple of angstroms in thickness. And at that point, you either will get a surface reaction or the reaction will not happen at all. And this is the part that we don't know exactly. At around 6 bars, what should happen is that the flame would still be there, but relatively close to the surface. And then we hope that the thermophoretic forces will be enough to deposit most of the aluminum oxide on the particle. That requires a little bit of hoping and a lot of uncertainty.
Wow. Impressive.
That's why we do research, right?
Exactly.
It's a fundamental research grant from the ERC project.
That's also a nice introduction. By the way, thank you very much, Thijs. But that's also a nice introduction to our next speaker. But let's first give a hand to Thijs for his contribution here today. That was a nice step up because Jeff gave the global overview. You took the deep dive in combustion on the research side. But let's also look at the other side. And this brings us to the first online presentation. I want to ask... Can we go? Do we have... see that. Welcome, Yvonne Boyerle. You can see the audience, I guess. We can also
yes,
see
I can.
you. We can also see you on the screen. We also see your presentation. And you're going to take us a step to the more practical application side, using the aluminum water reaction for peak heat. No, not heat, probably. Demand in buildings. But you're going to tell us about that. The floor is yours.
Yes, thank you very much. And it's a shame that I cannot be with you, but I'm happy to present anyways in this online in this case. So my name is Yvonne Boyerle and I'm a project leader at SPF, the Solar Technology Institute at the Ost. We're a University of Applied Science and we're placed in Eastern Switzerland. And so I'll introduce you to our Horizon Europe Reveal project, the revolutionary energy storage cycle with carbon-free aluminium to cover winter heat and electricity. And first, I'll introduce you to our consortium, then I'll explain our motivation and vision of the project, and after that, I'll present the concept a little bit, and finally, I'll go into details about our Alu2Energy prototype. And there you go. So the Reveal project combines 9 partners from 7 European countries. Partners from Iceland and Norway, they developed the technology for the production of CO2-free aluminium. Partners from Slovenia and we at Ost, we developed the Alu2Energy process, where we also include fuel cell engineers. Life cycle assessment is done by Pre. Our Dutch partners, they're placed in Utrecht, which we should have been there last week actually, but there was a strike with the trains and we could not go there. So we actually, the only partners who weren't there were we at Switzerland, because we wanted to travel by train. That didn't work out, but yeah, anyway, so the Ratsverterm is our German SME partner, and they analyze for us the market opportunities. And last but not least, Phoenix, they from the Czech Republic, and they are responsible for communication and dissemination tasks. And I'll brought you here the heat demand profile of Switzerland, which we project is in 2050 about 55 terawatt hours. So this is for space heat and domestic hot water demand, with approximately 80% of this demand is needed in winter months, so from October to March. And we can see also that the domestic hot water demand and also in process heat for the industry, they stay relatively steady throughout the year. But the key challenge really is supplying this large seasonal winter heat demand, especially using renewable and carbon-free energy sources. And this leads me to the central question: where will our winter heat come from in a carbon-free energy system, given that renewable electricity production is limited during the winter months? And here's our vision. Let's take the winter energy demand for a typical single-family home of about 11,000 kilowatt hours. In the past, we used heating oil. We burned it. For that amount of energy, we needed to store about 1 cubic meter of heating oil, which is really, really small considering other alternatives. But yeah, we burned about 2 or almost 3 tons of CO2 every winter in this case. And today we can store solar heat in water tanks during the summer. This works very well, but storage size is significant. We can also try to store PV electricity in batteries. We'd need around 30 cubic meters of volume. That's also very huge, but not only very huge, but it's also very expensive. And this where exactly Reveal comes into. We imagine that this winter peak demand is covered from aluminium. In this case, in our case, aluminium granules, and then we only need 0.75 cubic meters of storage volume. So much more compact, clean, and potentially cost-effective to cover this winter peak demand. Now, there are different ways of aluminium that can release energy, and you heard the first 2 ways. It can be burned in air. This creates very high temperatures, over 1,700 degrees. Jeff was talking about it, but it can also react with steam, which Thijs talked about it. Also, higher temperatures. But for building applications, we're at temperatures of about 60 degrees. So the reaction with liquid water here is really the best fit for our application. And I'm not going into details here. I'm pretty sure you are familiar with it. But let's have a look how we apply this within our Reveal consortium. So the goal is for Arctus and IceTech, our partners in Iceland, so they're the aluminium experts, with the support of Sintef, to produce aluminium using only 13.5 kilowatt hours of renewable electricity per kilogram of aluminium. And this without carbon emissions, of course. And aluminium is then transported either to Slovenia, where it's to our partners at NIC, where it's used in the aluminium steam reaction for industrial applications. So they also look into aluminum steel reaction, but also, of course, aluminum is being transported to us at Ost in Switzerland, where it's used in the aluminum water reaction, as I said, for applications in large buildings such as multifamily homes, service buildings, or building complexes. And both generate heat and hydrogen, along with either aluminum oxide or aluminum hydroxide as the reaction product. And the hydrogen can be directly, let's close the cycle first. Aluminum hydroxide, in this case, needs to be calcined to regenerate aluminum oxide and close the material loop. And the hydrogen can be directly converted. This is what we do. We don't want to store, like it doesn't make sense to store hydrogen or large quantities of hydrogen, in our case, in the buildings. We really want to directly convert it because we're only producing it when its energy is needed. So we use fuel cells, and at the end, we can totally generate approximately 2 kilowatt hours of electricity and 6.5 kilowatt hours of heat per kilogram of aluminium. And we at Ost, we submitted a patent last year for this Alu2 Energy prototype. We'll have a look at right away. But first, let's have a look how the green production of aluminium works. In this diagram here, you can see the low temperature electrolysis cell developed by Arctus. It operates at around 800 degrees, and unlike the conventional Hall-Héroult process, it uses vertical inert metallic anodes and wettable ceramic cathodes. So this eliminates the need for carbon electrodes, such as is used in the Hall-Héroult process, and of course eliminating therefore the direct CO2 emissions. Their benefits are quite substantial. We have 0 CO2 emissions, which avoids also carbon taxes and compliance costs. There is 20% lower energy consumption. The modular power input is also more flexible than the conventional cells. It can operate during low electricity prices or renewable energy surpluses. We can ramp up the production then and then ramp down the production a little bit when the prices are very high. Also, 50% less space is required for the same production capacity and 40% lower capital investment. And last but not least, 30% lower operation costs because in a traditional Hall-Héroult process, the carbon anodes are being used up and they need to be replaced and maintained regularly. So one of this big challenge also was to precisely control the aluminium oxide concentration in the molten aluminium in the molten electrolyte. And to address this, SINTEF has developed a novel in situ sensor that allows now for real-time monitoring of this alumina level, which is very essential for this step towards this efficient and fully automated green aluminium production. This concept was proven already in 2018, and last year, within the Reveal pilot plant, it produced first batches of green aluminium, and I also have one here. So for us, this is very, very exciting, and but there's still quite some development that needs to be done. But we expect commercial sales are available within 2030. So with this, I'd like to go into details, a little bit more into details about the aluminium to energy development. And we don't use powders. We don't also use these large batches. We use granules, and they're larger than 1 millimeter in diameter. And here you can see from the top our 3D model of this 4 kilowatt Alu2 energy prototype we developed, or designed, developed. Now we also commissioned and had some first tests. And it consists of the main components of aluminium storage container, the reaction vessel, a crystallization vessel, also a hydrogen buffer tank. It's rather small, but we just put that in so for the fuel cell we can have, if we want to, a continuous flow for some time. Then there's the fuel cell system, the control cabinet, and last but not least, the sedimentation vessel with also the aluminum hydroxide collection container. And this is how our system looks like. So on the left, you can see the overall frame. Everything is placed in this frame. In the middle, it's a close-up of our reaction vessel, and on the right, you see the hydrogen tank with a fuel cell system. And I mentioned we just had commissioning not that long ago, and but we had also some experiments. So here you can see a diagram that shows a brief snapshot of an experiment we did lately. You can also see that the temperature control parameters are not yet optimized yet, resulting in this oscillation pattern. Then the temperature of the reaction vessel here in orange was set to 65 degrees, and the cooling cycle in yellow and blue was operated to maintain this target temperature. Now for the hydrogen production, the line in green with the axis on the right, indicate that we reached up to 6 norm liters per minute with an aluminium feeding rate of 4.5 grams per minute. Our maximum is for this system 8 grams per minute. And you can also see these frequent drops in the hydrogen flow, indicating that a saturated sodium hydroxide solution containing aluminium hydroxide was periodically exchanged. So we could crystallize them and eventually collect them in our collection vessel. So under conditions as assuming 100% conversion, 1 gram of aluminium can produce up to 1.25 liters of hydrogen. Therefore, our 4 kilowatt Alu2 energy prototype can theoretically produce up to 10 norm liters of hydrogen per minute, and in this case we can maximally achieve 1 kilowatt of electrical output. And with this, I like to summarize. For the power to alu process, inert anode electrolysis cells, they enable aluminium production with zero direct CO2 emissions, powered entirely by renewable electricity. So in Iceland, they have hydro and geothermal electricity, and this development is on track, and fully commercialization is expected by 2030. For our Alu2 energy process, OS developed an innovative aluminium combined heated power pilot plant generating 2 kilowatt hours of heat and 2 kilowatt hours of hydrogen from aluminium. 3 kilowatt hours of heat. This is a mistake, and 1 kilowatt hours of this is hydrogen. Electricity is 1 kilowatt hours, but with hydrogen it's 2 kilowatt hours. Sorry. So for winter peak demand covered in Central European homes, we need 500 to 1,000 kilogram of aluminium per dwelling. That's less than 0.75 cubic meters because we reach 15 megawatt hours of per cubic meters of energy density with our granules. The aluminium concept enables 100% solar-powered multi-family homes, providing both heat and electricity with complete seasonal energy independence. And by 2030, we project realistic energy costs of 30 cents per kilowatt hours for end users, which makes it as a cost-effective solution for renewable energy storage. We also have to consider here that in the future, this winter energy will become much more expensive, especially compared then to the summer, because prices go with demand and supply, and so we see this as this solution, really as a revolutionary and high potential application. And I'm actually finished now, but I'd like if you like to stay tuned, we'd love you to follow us on LinkedIn or any other social media platform. Just remember the terms reveal storage. And with that, I'm really at the end of my presentation and happy to answer any questions.
Thank you very, very, very much, Yvonne. Great work you do at OST over there.
Thank you.
What you couldn't see is we had a moment here where we were looking into our hydrogen chamber, where there's a setup from Team Solid, the student team in Eindhoven that's working on iron wet cycle, let's say. But the setups that you were using and that they are using were very much alike. Yeah? So it was beautiful to see that at many places around the planet, this type of research is going on. We're all trying to find or contribute our way into energy transition as well. What I especially liked is you're making this very practical. You go into the homes of people. And this is to where I said in the beginning that market traction is really picking up if we manage to reach that point. Yeah, because then we'll all be affected and we'll be probably very happy. What was even better is you promised a price, because we won't forget that, of course. Your promise now, 30 cents per kilowatt hour. The maximum we're paying in the Netherlands now is 39 cents. So you're well within current market conditions. Of course, the world wants us to do better than what is the state of the art now. So our ambition should be to go even below the 39 or the 30. Yeah? But the best part for us is that we're also making these calculations at our end. And yes, we're coming to similar pricing levels. And that makes innovation fun also, that there is also a point in your development where you realize, gee, we're really going to nail this. Yeah? We're not far off anymore. We will really get there. Yeah? And yes, there will be a point where you can compete with people who have worked and optimized 100-year fossil technology, and us standing up and saying, okay, yeah, let's race. We'll see. So thank you very much once more. Also, questions for you from the audience.
I have from online, from Dan from ArcelorMittal. He asks, can the process accept intermittent renewable energies?
Yeah, so we looked into this, and the aluminium experts, they're, let's say, they're kind of stuck in their old ways also. We're actually coming to them and we're challenging them and telling them, okay, you guys, you have to make this work. But because, I can go into details. The electrolyte, there is this, it will freeze at some point, right? So you have to keep it within the temperature. And with the Hall Herald, this temperature band is only very small, like 10 degrees Celsius. But with this new technology, it's 90 degrees. So it depends also, does it still, can we isolate it or not? The electrolysis cell at the moment, you cannot isolate it because there's aluminum oxide ledge at the side walls. Otherwise, the electrolyte would eat up the side walls, which is not a good idea. So actually, heat needs to be dissipated. So this is why these old traditional cells are not very efficient. But now we're looking, well, we're pushing them to go move forward. They are looking into other materials that can be used, so we can actually insulate the cell. If they're insulated, then this becomes even, this 90 degrees, you know, I mean, you can go then for longer periods of time. On the other hand, I have to say, we also came to them, we said we want to produce only in summer. Yes, but we're kind of naive in this way too, because we notice also with the electrolysis, hydrogen production, I mean, you have a capex, and if you only operate it in the summer, you know, then it just becomes expensive. It's we have to. I mean, I don't say it in the future. It won't be possible, but there's a lot that still needs to be done. We have to rethink, but I guess one step at a time.
Another interesting question, though, a small one. Many thanks, by the way. Got the receipt here. What will be the size of the solution in the homes?
Yeah, so of course the prototype you saw here, this is not optimized within the space, let's say. I mean, of course, we designed it in a way that we just could have easy access, and it was just easy to handle for us. But of course, it needs to go down in the size. And I mean, you saw there was lots of empty spaces. At the end, it won't be larger than like a heat pump system now, or thermal, let's say thermal storage in your house unit.
Thank you.
The typical questions when I sit in talks with customers that I would get at this point is people looking at me and saying, "Why aren't we doing this already?"
Yeah.
And you go like, yeah, that's very motivating, but also frustrating.
Yeah, and I'm really happy. I mean, we also have a spin-off company now, and yes, so now it's a very exciting time for us. We really want to go into market as soon as possible. We're planning in 2027 that we will have already some systems in the field, and yeah, we're on it.
Wow, wow.
We're really trying.
Any
hard,
questions
yes.
from our audience here? Mo? Oh, now it's going to be interesting.
Thanks a lot for the nice presentation. It's Mo from Armantech. So I was wondering about water cyclicity here. And for example, a 1 kilowatt burner, how much water it consumes. And if we want to have a full cycle for a home application, it means both production of aluminum and also energy production from that. What do you think a storage tank for the water would be if you want to go to the seasonal, basically energy transport where you basically can have a full water cyclicity? Thanks.
Very interesting questions. So for us, I mean, we're in close, well, our partners from the aluminum industry told us that small electrolysis cell, especially in homes, they don't see it. At least not now or in the near future. So this might be, at the moment, this is a fantasy still, and we kind of don't have the time to look into this. Like we have to focus first on this development. So I unfortunately don't have an answer for this question at the moment.
Happy, Mo?
Yeah, sorry.
No. But any other questions? I see more hands. No other burning questions. Yvonne, thank you very much. Big hand for you
You're
as
welcome. Thank you, and yeah, enjoy the afternoon or evening, yeah, and maybe see you some other time.
Thank you very much.
Okay, bye-bye.
We'll move to the next presentation, being live here on stage again. Michiel Cruijff is meanwhile joining us. I know Michiel as a, coming from, well, both our careers started probably at the same point, but you started on the ESTEC, ESA ESTEC side. And you've always been on the high-tech development side, the development cycle, and the entrepreneurship, the big split. Today, you're going to make us part of your undertaking now in what you've already introduced a little bit. They're also producing electricity. And you're taking this further, probably.
That's
Michiel,
right, yeah.
introduce yourself and
thank you, Raoul.
tell us.
Thank you also, Yvonne, if you're still there. We should definitely talk because it was super interesting. We're doing something that, connects very well to what you're doing. And everybody here, I'm Michiel Cruijff, the CEO of ZemQuest, which is a startup. We started last year. And actually, we were starting because of the demand from the user. They came to us and asked us if we have a solution. So we have a vision for professional working sites that are remote and large vehicles to also be running emission-free. Cheaper, safe, and hassle-free. And we would like to do that by selling solid fuel. So large construction projects run into a bottleneck for their electrification. I mean, there's strong market drivers to reduce emissions on remote working sites. There are financial incentives, there are regulatory constraints. There is also a sector drive. The sector itself really wants to electrify. And there is, of course, the environmental impact reasoning to electrify. But yet, there is this bottleneck. Electrification requires energy. There are developments, major improvements continuously ongoing on improving batteries and on-site storage solutions. But any single battery needs somehow to be charged. And for that, in some way, energy needs to be transferred to the site. So if you look at the typical large construction site, like we have hundreds of these in the Netherlands, they need about 5 to 10 big machines, and each of them requires to be electrified, and the energy for those machines need to be transported and somehow transferred to those vehicles. That is about 2,500 kilowatt hour per day that needs to be transported and handled, which our customers and user partners tell us that's a gigantic daily and costly hassle. They're currently doing that with lithium ion, which has low energy density and therefore low endurance, and therefore requiring a lot of logistics, this daily logistics. To be charged, these batteries need to be charged off-site, where there is no net congestion or where the grid is strong enough. Plus, they have a fire hazard. This results in the energy price, effective energy price in these remote working sites, of 1 to 2 euros per kilowatt hour, 5 times the price they're actually paying for the electricity. And all that difference is sitting in those logistics. Hydrogen is being pushed as an alternative. Our users are not too excited about it. It has the same problems. It requires even more complex infrastructure, even more safety and transport limitations, also regulatory. The price is even double that of lithium. So these numbers actually didn't just make them up. We went into discussion with these user partners and went through their particular use case, all the steps, and the actual cost, total cost of operation for these cases. So it's costly, a lot of hassle, and not sufficiently safe. That's why our value proposition is to bring emission-free energy to the site that is more compact, safe, and hassle-free, using aluminium as a circular fuel. That value proposition is not only useful in the construction world, but also in other businesses, like mining, container transport in harbors, autonomous agriculture, and transportation in airports, and even aircraft themselves. All these applications have in common that they would benefit from having higher endurance. And we can deliver 5 times higher endurance due to the higher energy density. Our solution is compact and very scalable, and this gives you less operational hassle. So less downtime and eventually the opportunity to operate 24/7. Therefore, at lower cost, and with a technology that is non-flammable and non-toxic, and meets the sustainability requirements by having no CO2 or NOx emissions on site, and with Ivana's technology also not in the full cycle. And we use 50 times less rare earth minerals than lithium-ion battery storage solutions. So how does it work? We make use of the high energy density of aluminium. We're able to extract 2.5 kilowatt hours per kilogram of aluminium, and in the form of very simple plates. So they're easily produced. They roll off the rollers, and we cut them in plates. They can be a little bit crooked, doesn't matter. Together with cathodes, salt water, and air, we stick them in series and generate a battery like that produces electricity. And as a reaction result, we have the aluminium hydroxide, which we collect after use and recycle to aluminium. Then we insert on-site fresh aluminium plates into the fuel cells. So we can keep on working. This is an ongoing process. That's the concept. These are the targets that we want to achieve. Less than €1 per kilowatt hour, less 1 kilogram per kilowatt hour, and less than 1 liter per kilowatt hour. So I like to have simple goals. And more than 1,000 uses of this cathode battery. And then the energy density target is 2.5 kilowatt hour per kilogram that we can extract, and that we have already met. So we have this prototype design that we want to demonstrate out of the lab soon. So far, we have this only demonstrated inside the lab. So we have some steps to make right now. Our technology is patented. It's designed to be modular, so we can scale up for large machinery. These cells that you see there are actually the size of the cells that we would use for very large excavators, things like that. This is made possible by our concept for fast and on-site reactivation. So we can essentially retank the fuel cells with aluminium. In the lab, we demonstrated the energy density, also the power density that we need for these machines. For example, for aircraft, to fly an aircraft for 10 hours, you would need about 5 times higher power density than we achieve right now. So there's a step to make, but it is also within range of possibility. So far, we've been running it for 10 hours, including stops and restarts. So we have that capability as well. It's fully designed for circularity, which means it's non-toxic. We only use single components of single materials, large components that are easily disassembled and recycled after this 1,000 uses or 2,000 uses. So the market for this is really huge. If you see there on the left, I mean, these are all the applications I've shown you before. On the left, a market of 2 trillion sounds not realistic, but we're not actually looking here at machines or new electric vehicles that are being procured, or even the batteries that go in them. We're not selling batteries. It's about the energy that these machines, these new electric machines, will be consuming in future years. And every year, or every day again, every machine is using 500 kilowatt hours. So that adds up to a massive market potential. And then if we look purely at the market for our aluminum batteries, it's a subset of that. Then actually the obtainable market is not shown here. It's about 1 billion within the Netherlands, Germany, and Belgium. And that actually is a market that's so big already that we cannot supply it ourselves. So within, let's say, 5 years from now, we would be able to achieve a market of 200 million euros with about 40 customers. So a very low number of customers of the type that I showed you before would already have such a revenue, which would allow you, hopefully, to eventually invest in having our own smelter, and a green smelter. So our business model is to provide energy as a service, so circular energy. We cannot do that alone. We are essentially technology developers at this point, so we need partners. We're partnering with VDL for building those batteries, with Quintech Energy for delivering the front-end interfacing with the customer, Jan de Rijk for the logistics of transporting these to the customer. And then our main business model would be in the reactivation, so in putting new aluminum plates inside and recovering the waste, which we then send to be recycled. And right now we're working with Alludium and through them with the Norsk Hydro for green emission-free recycling. In our financial models, we made a breakdown of the different cost components, and as soon as we managed to automate the reactivation, for which we have our concept developed, we would be at about €1.30 per kilowatt hour. So that is already, in these entry markets, an attractive pricing. As we scale it up to multiple reactivation lines and going to on-site reactivation, we can go down to 80 cents per kilowatt hour. And once we invest in our own smelter, and we would be able to use renewable energy at low price point, we can go down as low as 25 cents per kilowatt hour. And this with sustainable level CO2 emissions and a full cycle efficiency that is lower than hydrogen, which is a bit our competitor. So how do we plan to go to the market? I mean, we're clearly startup, we're at low TRL, we still have to go out with the lab. But the product we're working towards, the first product is containers that we stack full of these cells, thousands of these cells in convenient boxes for on-site charging. This is also where Quintech Energy has their business model, and we work with them to deliver these containers to sites where they can charge electrical vehicles, excavators, and such from the containers. Then we actually, once the batteries are used, we pick it up and reactivate it in our own facilities. In the next step, we would reactivate on site itself. So we have a compact solution, also containerized, where the batteries, consumed batteries, can be reactivated with fresh fuel plates. That allows you to store all the energy need of a large construction project, talking about a few hundred megawatt hours, in only a few containers filled with aluminum plates. And this is, there's nothing comparable, no comparable way of energy storage where you can store a full large project, half a year of 10 machines running, in terms of energy on site. So that would be the next step. And in the third step, this is additive. On top of that, we would actually develop batteries that can be placed on vehicles as range extension. So they would work in unison with a small lithium-ion battery, and essentially keep that lithium-ion battery charged continuously. And with that, you can achieve 24/7 operation of vehicles like AGVs, autonomous guided vehicles, in the Rotterdam harbor. or excavators or mining machines that need to work 24/7. And finally, we can expand way beyond that. We have, for example, our partner Exceed, who is very interested in having a lightweight energy solution to put on board of their autonomous agricultural machines. If you have these lightweight batteries, they can work continuously. Right now, it's not doable with lithium ion, and lithium ion is so heavy that the machines sink two-way into the soil. So this is for them, the solution that they need. They say, if you have it now, we would buy it. Even at that price point, we really would want that technology today. In the roadmap, it's a bit more complex because you need to develop the machines together with the batteries. But once you're there, you can also think of electrifying trucks or even aircraft. So this is the team. Right now, through an unfortunate event, I'm the only person in the company as CEO, and I'm supported by TU Delft, by Assistant Professor Momita Rana, who's doing the research and the scientific research. We have several engineers supporting us on the design. And importantly, we rely on our partners for the production and the service provision in the future. And I think that gives us a good starting point to actually, in the coming year, go out of the lab and demonstrate this on an actual vehicle. So, thank you.
Well, Michiel, really impressive. I could imagine there are no questions because everyone is scraping their head and say, wow, didn't see that coming. Yeah? An entrepreneur being that far, taking all the risk you can take, and just do it. Yeah? So congratulations on that already. Are there any questions that we want to ask online first?
There are. These days, heavy construction machinery have moved away from diesel to electric-powered CNG, LNG generators. Have you done a comparative study with this?
No. No. As I said, we have looked at hydrogen fuel cells and lithium ion, and that's essentially what our current customers are using. And also what these customers that I've shown, they're really front runners, they're very experimental. They want to try out the new technologies. So this is what they've been working with. But indeed, green fuels, that's an alternative. We have made, let's say, back of the envelope comparison with these. But also there, the production efficiency of these fuels is quite low. So, but of course, in terms of energy density and practicality, we cannot really beat using green fuels.
Thank you.
Any questions from our audience? Jeff?
Thank you, Michiel. A very interesting presentation. I think the aluminum air battery is obviously a very interesting alternative to the kind of combustion routes or reaction routes that we're looking at. Questions that I have, I've got many, but maybe I'll just focus on one. What's the purity of the aluminum that you need to run the battery? I presume it's pretty high purity.
Yes, right now, well, it depends a little bit which technology we use. So we've used the alkyne electrolytes, then it's not very high purity. Right now, we are working with reasonably pure, so I think 99.5 and up. I think the best performance we reach at 99.8 and up, so that's indeed right now our challenge. That's also where TU Delft is looking at how can we work with lower purities, because that would definitely drive down the cost.
Can you?
Yeah. Hi. Thank you, Michiel. On building sites where you actually have a grid connection, where you would be able to charge batteries during the night, how competitive would you then still be?
Well,
because you won't have the transportation cost of the batteries.
Yeah, it's a bit hypothetical. I mean, it's not hypothetical. It's not the business case that we're looking at, right? So for these large infrastructure sites, building dikes, etc., the net is just too congested in the Netherlands to allow multiple machines to be charged.
Okay. And maybe a second question is
but yeah, if you want the price point, that these fast charging, if you would be at such a point, it's about 60 cents per kilowatt hour that you would have to compete with. Eventually, you saw the development path. We would be able to compete with that because we have very low capex. Essentially, the users don't have to buy these big electric batteries if you put essentially our systems. Our batteries are really cheap. They cost a few €1,000 instead of a few €100,000. So the cost is the refueling them with the aluminium.
Maybe second question, what is the power in terms of the amount of kilowatts that you can get out of the battery?
Yeah, the power density is much lower than with lithium, but well, the best lithium batteries have maybe 10 C discharge capacity, but typically it's a few C, and we're more at 0.2 C or so. So an order of magnitude lower than lithium. And that's why this technology is, I think, not very suited for private vehicles or so, but for these large machines that require endurance. Because then you put a lot of cells, and you can also then support high power because you have many cells, but you have the endurance.
Okay.
Any more questions?
Very quick question. A container of those cells, how many megawatt hour do you expect you can store in one container?
So in one 10-foot container, theoretically, we could put 60 megawatt hours for extractable energy. Practically, 25 megawatt hours would be our design target.
No one else? Then I think, Michiel, thank you very, very much. That was nice and interesting. I think we have explored aluminum to the point where we say, well, we've seen business cases, we have seen where it started, and research, or deep research in between. Let's take a short break. Also to the people online, go run to your coffee machines now. In 15 minutes, we'll be back and continue with another metal. Okay, I propose we start because we don't want to get more behind schedule. We promised to go into other materials. The first one we have lined up after the break is magnesium as an energy carrier. A presentation that will be given to us from another international partner in the consortium, or in the ecosystem, Université de Haute-Alsace. Cornelius Schonenbeck. Are you online already?
Yes.
Yes, can you hear us well?
Very good.
Super. The floor is yours to enlighten us on magnesium.
Thank you very much. I have an echo. So I will present you our work on magnesium air combustion as new source of clean energy. First question, why magnesium and not other metallic fuels? On the one hand, magnesium is quite abundant on Earth, about 2% of the Earth's crust, and as well in water. The energy density is comparable to other metallic fuels and as well on hydrocarbons. So it could be a good choice. What are the particularities of magnesium? The particularity is that the melting point and the boiling point are very low compared to the flame temperature. So what we have seen, the combustion, the fast combustion will always be a vapor phase droplet combustion. Only when we reduce the temperature very low, below 650 degrees, we could have a real heterogeneous reaction. First, I will speak on the homogeneous combustion of magnesium, the fast combustion in the magnesium air flame. I will skip the experimental setup. We inject magnesium powder in the center of our reactor axially and tangentially the secondary air to create a swirl. The geometric swirl number obtained are between 0.7 to 8.4. The equivalence ratio from 0.15 to about 1, so from very lean combustion to about stoichiometric conditions, and the power delivered varied from 5 to 25 kilowatts. What was our objectives? First, we would like to obtain a stabilized magnesium flame. Second, we would like to know where does the solid is going. And third, what are the byproducts, what are the pollutants who are formed. To do this, our experimental device at the reactor, a cyclone for particle capture, a secondary heat exchanger, afterwards analyzers to analyze oxygen and nitrogen oxides. So where does the particles are going? Here a little video on the video. You see the flame is very bright. Where does the particles are going? We have recuperated all particles in different parts of the reactor himself, the cyclone, the elbow connecting to the secondary heat exchanger and the secondary heat exchanger. The major part of the particles is recuperated in the main reactor and the cyclone, a smaller part in the elbow and the secondary heat exchanger, but there's always a part going out. But considering that it is droplet combustion, there is possibility to create nanoscale particles, and then it's quite good that we recuperate as much. So, second question, what's the size of the particles and what does they look like? The size of the particles, we have made a laser granulometry of the recuperated particles. We see that almost all are in the micrometric scale. In the small micrometric scale, about 20 microns for the most representative size fraction. What do they look like? Their microscopy was helping us. On normal electron microscopy, we can see a foamy material, which is an agglomerate of aggregates of magnesium oxide. These agglomerates are sized from, I would say, 5 to 150 micrometers. When we go nearer with TEM, we see that the crystals are magnesium oxide crystals, and they are cubic. These crystals are in the nanometric scale between 50 and 500 micrometers. So we see that most of the particles are agglomerating, so it's not necessary to prevent formation of nanoparticles, but perhaps it would be interesting to have conditions where the nanoparticles can agglomerate, because after agglomeration they are more easily to capture. Now I will go to the second pollutant, the nitrogen oxides. Nitrogen oxides can be formed, as you have seen, the reaction is very bright, temperature is very high, and so thermal NOx can be formed. The highest temperature we have measured in the system is the particle temperature using an optical pyrometer, and the observed temperature are between 2000 and 2200 degrees. They vary. The variation with the equivalence ratio is small, and as well the variation with nitrogen dilution is relatively small. When we measure the quantity of NOx formed per kilowatt hour of energy produced, we see that there's always obtained maximum for global equivalence ratio between 0.5 and 0.6. But for our global equivalence ratios, the quantity decreases. The quantity of NOx formed decreases as well when the NO dilution was increased. So this gives two possible solutions to reduce NOx emissions. One is to work at near stoichiometric conditions, and the other to use flue gas recirculation. So we can reduce. How does we explain this compartment? Normally, we would attend that for higher concentrations, the NOx quantity is big. When we see the particles are initially cold. They are heating up by graduation and convection, and afterward they are burning. But the burning rate of the particles is very, very fast. So the consumption of oxygen by the magnesium oxidation is very faster than the production of thermal nitrogen oxides. So nitrogen oxides are mainly formed after the final oxidation of the magnesium, and then in the vicinity of the particles where the heat is, there is no more oxygen, no NOx formed. So we see it's possible to reduce NOx concentration by different methods, mainly working near of stoichiometric conditions. To know where's the reactor, where we have to measure, where we have to place our measurement devices, we have as well made a cold flow simulation of the device. You see here the recirculation zone inside, permitting to know where the flame could stabilize, and we have made this simulation for different swirl conditions. Now I will talk a little bit on the heterogeneous combustion of magnesium. For this, we have worked for temperatures below 600 degrees C in a small fluidized bed. We heated the bed at a constant temperature between 530 and 570 degrees, and afterward we switched and we added oxygen. And on the left-hand figure, you can see the normalized extent of conversion during time. As attended, the velocity of increases when the temperature increases. For all three temperatures, we see a sigmoidal graph indicating a nucleation process. We see as well, when we see with microscopic imaging, we see that there is quite a difference between the reaction products, between the lowest and highest temperature. On the lowest temperature, particles maintain their initial size. They look a little bit like a cauliflower, but at 570 degrees, there are great agglomerates, and we see spheres in the sample. Due to the sigmoidal curve, we have tested different models known to represent the nucleation process. Two sample models we are relatively simple and Rami-Hirofev of order 2 and 3, and the Mampel-Delmont model. The Mampel-Delmont model has two reactions. One, the nucleation rate, and second, the rate of growth of nuclei. The Mampel model is more precise, but the activation energy of nucleation, but the cost of computation is greater, and we see that the activation energy of nucleation is almost the same as for the Aramri-Evrofev model. The Aramri-Evrofev model is less precise, but for computational fluid dynamics, perhaps it could be more interesting due to a lower computational cost. To conclude, the laboratory scale combustion chamber shows that we can give design specification for the heat sources. It demonstrated that NOx emissions can be controlled and that more than 90% of the magnesium oxide produced is trapped in the system. For the down-fired burner configuration with a multicycline, there should be almost a better recuperation. For the slow oxidation of magnesium, we showed that it's possible to maintain the oxidation of magnesium in homogeneous phase, and that the size of particles is about the same as for the initial particles, mainly for the lower temperature. There is a changement for the higher temperature. Our staff, we have several theses, PhDs, beginning with 2015, and I thank you for your attention.
Thank you very much, Cornelius. Nice to see other metals also being used. Any questions? Let's first go online again, Michael.
No questions for now.
Any questions here? Oh, you go.
Hi. Thank you for the presentation, Bram Hakstegen. You mentioned the NOx emission and you compared it with a combustion engine, and I remember the lowest value was 1 gram per kilowatt hour that you mentioned, but legislation, at least in vehicles, is much more severe, and therefore they use a catalyst. My question is it possible also with your system to apply a catalyst behind the system in order to reduce the NOx emission even further?
In principle, it's possible to make a catalyst because we are near stoichiometric conditions, so a catalyst should work. We should not have the problem with diesel engines where we have to inject urea or other reducing agents. It should be possible when working at near stoichiometric conditions.
Yeah. And the second question is about the particles. Also for vehicles, there's particle counting numbers starting from 10 nanometer. Do you think you can meet those severe requirements as well?
We have worked partially on the particles, and we know that for the moment our system is not really optimized to stop them. So there is work to do, but it should be possible to create conditions where agglomeration takes place and then particles can be grown to limit these quantities.
Okay, thank you very much.
Our principal partner was Stellantis, so producer of automobiles, so it was a problem we addressed in our work, but which is not finished.
Jeff, one more question, then we'll move to the next presentation after this.
Thank you, Cornelius, for the presentation. So you've shown that you can do efficient combustion of the magnesium. I'm wondering about the closing the loop. So on the reduction side, what is your assessment of the state of the art in clean magnesium recycling, and who's the leader in that? Because I think that's a key barrier for this concept.
In our project, there was a partner, Promes, who worked with solar furnace to reduce magnesium. They used partly hydrogen, partly carbon of carbonized biomass as reducing agent at energy, solar energy.
Thank you.
Again, Cornelius, thanks a lot. What I found also very nice in your acknowledgements at the end, that I saw the name of Dries Laraki, apparently one of your PhDs, worked on the same technology as well. He's now running his own startup, and that's great to see that people stick with, let's say, the ecosystem and turn their ideas or their PhD work into business opportunities as well. Thanks a lot. Another hand for you. And then we'll continue with zinc. I see Ellen already lined up. Thanks, Cornelius. Ellen, now it's your turn. You're going to talk to us about zinc. I will warn the people here. You live very nearby here. You're at a daily commute to the big zinc factory here. So be careful with your questions. Yeah. Here's someone who knows what they're talking about. Ellen, the floor is yours.
Okay, thank you so much, Ro. Yeah, so I feel a little bit very practical subject. What I'm presenting. I feel a little bit all academic, a little bit out of place, coming from a factory that has been there for more than 135 years, of which since 1973. I'd say 95% electrified. So it feels a little bit funny. But so I'll first go through this is the 3 things I want to talk about. And I'll take you through and see what it means and actually what our connection is with Metalot. So I just needed to show this, and I see something is going wrong in the slide here. Because I see most of it is not at all coming through, but I'm not sure but that's okay. Nearstar, we have an international footprint. We have 4 smelters, 3 zinc smelters, 1 lead smelter in Germany, 3 zinc smelters in Europe, a lead smelter and a zinc smelter in Australia, and mines, zinc mines and a zinc refinery in the US. And we're wholly owned by Trafigura, who is a trader. And commodity trading, supply chain, logistics. So close here in Budel, we're obviously here in Budel. Most of you must have seen it while you come here. There's, you drive along a beautiful canal and open fields, and suddenly you see this big factory standing. Budel Zinc can do about 300,000 tons of zinc per year, and we're one of the biggest smelters in the world. Also, I do believe one of the most energy efficient smelters in the world. We have our sisters companies in Balen-Pelt and Aubie, and obviously we have a lead smelter now in Stolberg. So what do I want to talk about? Now, so this slide is not at all coming out, so I'm not sure what is happening, Michael. Is it showing the same on the screen there? Oops. But I'll talk my way through it, no stress. So I guess what is standing here above is our existing flow sheet. So what do? We take in zinc concentrates, zinc sulfides, we have some secondary materials, zinc oxides. Obviously in these concentrates and oxides, the whole periodic table is present. What we do is we make a very pure zinc, which we then convert into the different zinc alloys that the industry wants, mainly the steel industry. And then we also make copper, cadmium, cobalt, nickel, manganese. We all recover that separately and sell them off as cakes. We make cadmium metal, but the rest is more or less part as a cake. It's a filter cake. There's other elements in it. And then the other thing we make, beautiful. We have what we call a bollop. It's the Budel Leeds product, which sort of has all the other materials in it that we haven't recovered. What is in there? There's quite a bit of lead and silver in there, which is valuable, and that goes to our lead smelters. There's, however, also quite a bit of iron in there. Now, lead smelters need iron, but not in the quantities that is in there. So they do make a certain amount of slag, which is, by the way, is being converted into something that is quite stable. Not an issue with disposing that. But now, what you must have seen in the news lately, a lot of discussions about critical minerals and metals. Now, in the Budel flow sheet, with zinc concentrate, so as you might know, this setting is that there's no such thing as a germanium mine. Germanium you don't mine as a germanium metal. Germanium comes with zinc. So when you mine a zinc concentrate, there's germanium in there. Now that germanium you could recover. Currently we are not recovering it. Why not? Over the years, because China has taken over that whole market, it has not been economical to recover the germanium. So what you have seen is that any zinc mines that were in Europe, any zinc refineries that were capable of doing this in the Western world have closed down in the last 30 to 40 years. So there is hardly any germanium capacity left. Umicore can make some germanium, Tech Resources makes some germanium, I should say, not uranium, germanium. But there's not a lot of them left outside of China. So what we have now said is, by the way, we could actually recover that germanium. That germanium is now, because our BLP has a structure, germanium goes into the crystal structure. You can't. We've got some Budel products lying here in the ponds. Once it's in that crystal structure, it's not impossible, but it would be very costly to recover that. But any new material that comes in, we could actually do something with. So we've come up the last 2-3 years, we've actively been looking at this, and there's some advantages in where it comes to iron. So what we're actually saying, instead of this one product that we make, we could make 3 different products. So first of all, we could make this critical metals concentrate, which would contain that germanium in a form that you could actually recover it. We would make a new, we call it a new bulb, that would actually be mainly lead and silver, and that could perfectly go to our lead smelters. And then we could then we have now this iron sulfur residue left over. Now what do we do with that? We could convert that into what we call now a clean jarosite. It's an iron sulfate. Now, for those of you academically, we know a jarosite is an iron sulfate hydroxide. It's got a fairly complicated chemical structure, but that iron sulfate could be quite interesting if it's very pure, because there is a market for pure iron sulfate. So this is in short a little bit where we've been looking at. So currently our jarosite containing all these materials, also some which you could consider being a little bit nasty maybe. Nobody likes the word arsenic. By the way, arsenic is a critical metal. Very pure arsenic is something that is being sought after. So what we're looking at now is we've developed this, what we call the clean jarosite flow sheet. And we're currently actually working on it. It's very live, this. What are our possible outlets? So what we figured now, this clean jarosite, could be a possible outlet is iron sulfur. The cement, the concrete industry uses an iron sulfate as a binder. So that could be a possible. But, you know, there is already, our initial market intelligence was there's enough iron sulfate on the market. Nobody is interested in this. But guess what? In the meantime, things are changing. So Tronox has closed their titanium factory in Rotterdam. They had a lot of iron sulfate as byproduct. There seems to be some movement in the market. Another obvious thing is iron. Convert iron sulfate into iron oxide and just make it as a feed material for the steel industry. Steel industry does not like sulfur, so that's not. So we'll have to convert it into a hematite. And then coming back, the lead silver would go to our lead smelters. A pre-hydrolysis product, so that is that critical minerals concentrate that would preferably go to our Neostar OB facility. Neostar OB has a indium factory, so any indium that would also be part of it, they could recover, and then they'll have to build that circuit, but they could recover the germanium. Within Neostar, that it sort of makes sense to split that all out. So we've been looking at this, and I just wanted to share some results with you. And this is more or less what we did on the clean jarosite. So if you look left, that is the clean jarosite. So by the way, we also got some interest from pigment factories. It's supposedly a very interesting yellow color. But we have found out that jarosite doesn't have a sort of, how do I say that? A cover, the cover percentage that it actually covers as in a paint that you could apply it, it's useless. Sorry. But we calcined it at different temperatures. We did this as a small company in Belgium at Resourceful, but we've also doing some testing at University of Aachen right now. And you see the beautiful color change to hematite, the nice red color. This, I have to say, this looks like a piece of charcoal. Actually, when you grind it up, it's perfectly red, it's hematite. Now, and so also what we did is, to make this clean jarosite, we need a one metal ion. In our case, we use either sodium or potassium. Now, that potassium is quite expensive, so we'd like to recover that. If we take this calcine and we wash it, we actually see that we recover most of our potassium back, which we could bring into our process. So that could be quite beneficial. So what would this actually mean? So actually this has been triggered by us because of other reasons, obviously. But why? What is the link now with Metalot? Is that obviously, and we've had discussions with Philip about this, could we use the clean jarosite directly in the iron reduction process that he has envisaged? It could be a source of iron for the iron fuel, the metal fuel process. The only problem, obviously, there's sulfur in there, and thus the off-gas system that has to deal with the sulfur. So that is something. We have looked now at making hematite. We've had some feedback from the Tatas and said it looks in principle okay. The problem is this is extremely capital intensive. And it looks at this moment so capital intensive that it's possible, technically it's possible, but commercially it probably won't fly. Unless the steel factories would want to pay us a huge fortune for it, which I don't think they will. Yeah, so that is one story. Now then, the other one concept that I wanted to discuss with you is burning zinc. So we've heard some discussions, we've heard from Jeff just now, and also again, we have zinc and zinc powder. Now, we produce our own zinc powder, we use it in our process, we use air atomization to make our own zinc powder from molten zinc. And for this, and especially when we want to make this critical metals concentrate and we want to make clean jarosite, we would actually like to have a very clean zinc oxide. Now obviously, because currently our zinc oxide feed is normally coming from the EAF dust, from the steel industry, and that is a bit, it's normally not as pure. And we would apply it at a point in the process where it would be very beneficial for us if we don't bring any other elements in the process at that stage. So we see a current shortage on the market for that zinc oxide. Now we have steam generation. The roast leach electrolysis process is self-sufficient. When our roasters are running, we actually don't need additional fuel input. But when one of our roasters is down, we have two backup boilers. So we could use some additional heat and steam. And having said that, one of Philip's graduate students recently did some work on zinc burning, and it's not a self-sustaining flame. So you need to actually fire this one up. Hydrogen, natural gas. We don't have a hydrogen line, but we do have natural gas, would be a more natural choice for us. So what would this mean? So we have our thinking is around two concepts, so that's why we are interested in burning zinc. First of all is obviously burning it and making the zinc oxide. The off-gas is not really an issue for us. CO2 we actually need. We have a bacterial effluent plant. We need CO2, we need H2. We could probably deal with that. The problem and we could use the steam. It's all perfect. The only problem in our calculations is that we find that we need about 2.5 times, the costs are about 2.5 times currently as an e-boiler. So for us at this stage, it's not really interesting yet to switch over. You know, this 5,000 tons per annum of zinc is for us not an issue, obviously, because we make 300,000. That's plus and minus for us. That's fine. And then the second concept is actually, and that more or less boils down also what was discussed here, make hydrogen and zinc oxide. Perfect. We currently have a reformer that uses natural gas to convert, to make hydrogen for our bacteria, to feed our bacteria. It's actually a very painful process. We would prefer to get rid of that. So we would actually like the idea of having, because we have zinc powder, we have steam on site. That would be perfect for us because that would be very controllable for us. But again, at the current situation, you come still about a higher cost for hydrogen. And plus, obviously, you will need some capex. We have an existing reformer. Having said that, that one is nearing end of life. So within the next 5 or 10 years, we probably have to work towards something. So then this could actually be a very interesting scenario for us. So, and I just thought so this is actually the end of my presentation. Yeah, I just wanted to give some practical inputs about what we, and why we've been involved with Metalot during the last few years. Any questions?
Let's go first online again.
I do. From Swiss Nanomaterials, do you have an estimate on the cost difference between refining freshly mined zinc ore into pure zinc compared to recycling pure zinc oxide?
Well, that's actually a cost that is not relevant for us because we would never be able to run only on zinc oxides. We would need zinc sulfides in our process. So there is one, I just actually had the discussion this morning with Jeff, there has been one refinery in the world, Scorpion Zinc, that was only treating zinc oxides, and thus you need to make your own sulfur. You need a sulfur burning acid plant, etc., etc. There has been one zinc smelter in the world. Again, that doesn't make sense. There's not enough zinc oxide in the world to currently build a smelter only on zinc oxide. So no, I don't have that cost.
Thank you.
Any questions from the audience? No. Then I want to thank you, Ellen. Very nice presentation. Thank you very much.
Thank you.
Also, also for leading up to our next speaker, Roy Hermans. When you introduced and started speaking about iron again, and maybe Roy, you may pick up from there, because you're going to tell us about another iron source that we may use.
Okay.
Roy.
Thank you, Raoul, for this introduction. Yes, let me check how this works. Yes. So, iron from iron sludge, I'll call it that way. So, put this project in a broader scope. So, we as university were looking mainly at the fundamentals. So, what kind of impact does impurities have on the combustion of iron, for example? But also, can impurities stimulate or make the combustion even better? On the other way, we are also looking, can we retrieve somewhere cheap iron? Yeah, so residual streams, for example. But one aspect that the water industry came to us is iron sludge. So the water industry is cleaning their water during the day. And typically they get about 90,000 ton per year on iron sludge in the Netherlands. Of course, the majority of this iron sludge is water, so you need to dry it. Typical components, or the majority of the components then is iron components, iron oxides, yeah, and then some residuals. Yeah. So in total, if you dry it, then in the end, and after reduction, you end up with about, let's say 5,000 tons of iron in the Netherlands. So in Europe, it's of course much larger. So in this project, we are looking at, can we use it in the end? Yeah? So for a starter, so the comparison. So this is what we typically use nowadays for burning our systems, 100 micron, slightly less iron, compared to the iron sludge, dried iron sludge. These are really, it looks like clay briquettes, pretty large, but easy to crush. It has about 50% of iron in it, and then, as I mentioned, several other components. So the water industry itself are looking for new valorization aspects of this iron sludge because it's for them a leftover, as residual stream. Nowadays it's going to the biological or soil purification or biodigester, but the regulation on that aspect are getting more stringent. So it's not anymore allowed to put in iron in these purification aspects, for example. So it has to be very pure matter that they can use then as iron sludge. So they're looking for other valorization aspects. So either as hydrogen carrier, so wet cycle as we call it also, or as metal fuel to produce heat or electricity. So typical particle sizes are mentioned here. So then high amounts of iron are desirable and so on. So we're starting this assessment now, what could be a suitable alternative compared to biodigester, or for example. The goal of this, what we called WISE project, is first looking at the reduction performance on a pilot scale compared to simply extracting the iron sludge from the soil in that sense. So small scale. Pilot scale is already larger scales, and find the optimal reduction conditions for groundwater sludge and surface water sludge. And give suggestions to Pometon for their large-scale reduction test in their facility, because the water industry already extracted a lot of iron sludge for testing for us. And in the end, we want to have a look at the is it economic viable? So how does it look like? So we have several sources where we got the iron sludge from. So one is location in the Netherlands is called Ossendrecht. It's groundwater iron sludge. And the other one is Andijk, for example, where we extract surface water. And then we initially did at the university material scan, what kind of properties are in it, and it's non-crystalline in that sense, and mostly we see ferrohydride. So then we had some differences between the pilot and the standard case. So the pilot shows much less contamination by organic carbon, for example. It's logical because there was an additional cleaning step in between that already extracted a lot of these components from them because it was already in their standard process. Pilot dryer pilot is drier than the non-pilot. I will show it a little bit more. And also the drying, I will go a bit more in detail in the next few slides. So the system that we use at the university is a small packed bed reactor for the reduction itself. So you have a small powder bed, heating around it, and then it's filled with hydrogen to start up the reduction. And with this pilot of small-scale reactor, we want to go in the end to Pometon for a larger scale. At the moment, I hope they are doing this testing. So it was everything is prepared for them. So around this time these tests will be performed. So I don't have the results yet from the Pomaton belt furnace. So in this reactor we put typically in about 7 samples, and we did a lot of these samples testing for the performance, reduction performance, and so on. A bit of a difference between the small-scale reactor and a large-scale reactor. It's mainly on the temperature range that we can achieve. That's a bit less at the university compared to Pomaton. But overall, we're try to compare and feed Pomaton with sufficient data to set their equipment in such a way that they can achieve sufficient reduction efficiency. So the approach to determine, first step is determine the mass change. So we need to have a real dry substance. And also we did a theoretical analysis on that. So first assumption what we took is that all iron atoms are in goethite form. But we know already, and I've seen it later on in different assessments, that this is not correct. It will lead to some errors, minor errors. Other components are negligible. So, and when we start our process to determine the different steps in between, we started with a raw material, so the iron sludge itself. We did a vacuum drying at about 200 degrees overnight. Then we have a dried powder, as I mentioned. It's already extracted the main water from that. So there's a small difference between the pilot and the non-pilot case. Then we stored it or did a calcination process with nitrogen in it at, I think, a temperature of about 600 degrees Celsius. Then we even extracted a bit more from the iron sludge. And then we did the reduction step, and we end up with even higher mass loss to get to the pure iron in that sense. So that's summarized here, where we changed the reduction time and various steps, where the blue bulk is first the drying at 200 degrees, and then the yellow bar is the calcination process, and then the last in the red, the reduction step that I increased in size on this side. So you see an increase in reduction efficiency over time. And if we could do a bit longer time reduction, then potentially we could achieve even higher reduction degrees, as you look to compared to the theoretical maximum. Then what we also did is similar for the different the pilot and the standard situation for the Ossendrecht iron sludge. And we increased also the temperature to some extent, so closely to our maximum temperature of 750 degrees. So we could achieve a reduction degree of about 80%. So optimal conditions, as we say at this stage, is 1.5 hours 700 degrees Celsius, but we know already from other tests that higher temperatures can still improve the reduction efficiency, reduction performance. So that's why Pomaton will use slightly higher temperatures in their furnace. Then related to the surface water sludges is a similar approach we took. And here we encountered this difference in theoretical maximum that I already mentioned that was an assumption that was not correct, and we need to revalidate that. So here we see that there's a difference between the both sludges and the reduction performance. So the Andijk has slightly higher reduction performance compared to the Lunderveen sludge. We're looking into the details of the composition of these sludges. It's not done yet, but that probably could give some insights in why the performance is higher in Andijk. So as a summary, the surface water sludges show a lot of more organic material and other impurities, so silicon, carbon, CO3, compared to the groundwater sludges. At a first glance, they do not seem to influence the reduction performance in itself, but we have to dig in a bit more into the details whether that's really the case. The difference between the groundwater sludges and the is small, and especially in the reduction over time and temperature. Both sludges, the reduction in performance increases with temperature and time. And with an increase in temperature, we see that, or we know that the performance is more efficient. The groundwater Ossendrecht sample is clearly better than the pilot. A standard sample is clearly better than the pilot. So do the applied filters of phosphorus compounds have some impact on the performance? We're looking into that. Yeah, as mentioned in the previous slide, that surface water of Andijk seems to show higher mass change. And yeah, there might be an indication that their reduction rate is similar to at similar conditions. Overall, the reduction degree by variation of temperature and time experiments has been as determined, but still room for improvement by applying higher temperatures. Especially, we hope this test at Pommeton will give a bit more insight in that. Then I need to thank very much Noah Jansema. He did all the testing, and Luc de Waal and Martijn Vechel from KWR, the water research company. Fortunately, Luc could not present today, so he's the main driver behind this project. And Konrad Hessels from the Eindhoven University. And the project itself, these are the partners that are working with us, and the money comes from the Dutch water companies. Thank you.
Thank you very much, Roy. Very interesting way of mining iron for our cycle, of course. Any questions, Michael? Any parties online?
None online.
No? From the audience here? Oh, we're ready for the drinks, I think. No. Roy, thanks a lot then.
Thank you.
I do ask you to stay here.
Okay.
And I'm also going to invite Ellen here. You know that every Metalot at Work, we also try to pay credits, let's say, to the people who have, in a particular way, facilitated the ecosystem in growing. And sometimes we have to reach these, or to hand these awards digitally to people because they're far away. Today, we are in the position to hand you one because you were away last time while we were all here. So we're handing you, Michael, if you can, the Ambassador Award, as we call them, for Spring 2025. I'm going to immediately ask you, though, to give it back to us. So enjoy it while you hold it, but it's only a couple of seconds now. Because you may have noted that as or since Michael joined us, that we have significantly worked on many things on the community side, but also on our branding. So the award you will get, which should fit your office nicely, is the one in the new branding. Thank you very much, Ellen. It's always great. Always great to have someone very nearby with a lot of experience, and especially as some of our installations, I should say, or applications reach the megawatt scale. Everyone can see the megawatt in this room would be quite challenging or impossible. Yeah. And yes, as an ecosystem builder, it's great then to have parties around that simply come to you when you ask them and they say, oh, a megawatt. Oh, and you said it here again. Peanuts for us. Yeah. So it's great that you facilitate projects. In this case, a project that we do with the French partner, Phoenix, and the German party, TS Elino or High Iron. And that, yes, you accommodate one of their installations. Fantastic. Thanks a lot. Well deserved. Roy, the reason I've asked you to stay here, of course, is you see Michael already there. Also, you have been super instrumental in a lot of work that you continuously do, basically, for us. And I think it was quite anonymous on our end to say, hey, if there's one person that we really need to thank a lot, it is Roy as well. You gave a presentation today, but this one is for the work that was all done before that. Thank you.
Thank you.
And let this also be a stimulation for other people in the room here, or in our... oops. Let this also be a stimulation for the people online that, yes, as an ecosystem we try to grow. Growing comes with doing more projects, doing more efforts, teaming together, building consortia. If you feel you can help there and you do, this is your reward. Thanks a lot. I propose we go to the drinks now, Michael. We have waited long enough. Sorry for the little delay that we have meanwhile, but the drink should be there. Thanks a lot.